Okay, so you'll notice in this lesson that the solutions to both of the examples we're going to look at are already in here. But I want to analyze and look at these a little bit more closely and just see how derivatives of these arc functions can actually be helpful, okay, and applied. So as we look at these, okay, one thing I do want us to remember is, just as a quick warm-up, let's review what our rules for the derivatives of the arc functions are. So we have the derivative of sine, and then we have the derivative of, not sine, arc sine, and then we have the derivative of arc cosine. We have the derivative of arc tangent and the derivative of arc cotangent. And then we have the derivative of arc secant. And we have the derivative of arc cosecant. And remember, it's useful to remember them in these pairs because if you know the derivative of sine, arc sine, then how is the arc cosine's derivative related? It's just the negative, okay? So, what's our derivative of arc sine of x?
U prime over the square root of 1 minus u squared.
Okay, good. And if u is just an x, then what is u prime? 1. Okay, so if it's just arc sine of x, it's 1 over square root of 1 minus x squared. Okay, and then the arc cosine is simply negative 1 over square root of 1 minus x squared. Okay, then we have tangent. What's our arc tangent derivative?
1 over 1 plus x squared.
1 over 1 plus x squared. Whoop, not x plus x squared. 1 plus x squared. And then cotangents, negative 1 over 1 plus x squared. Okay? And then, how about our arc secant? 1 over,
Absolute value of 1.
well, it's absolute value of x, right? Absolute value of x. And then times,
So x squared.
is he right? Square root of u squared minus 1, square root of x squared minus 1. Is that right?
Probably not.
You can look. Is he right?
So 1 over absolute value of x times square root of x squared minus 1.
Is that right?
Yeah.
Okay.
Okay, yeah.
Good. You guys should be double checking each other, okay? Think. Alright. So, we have that. And then the arc cosecant would then just be negative 1 over absolute value of x radical x squared minus 1. Okay? The secant, cosecant are a little easier to remember too. If you remember, what's in the radical is the opposite of what was inside the radical for arc sine and arc cosine. Any of those little connections that you can make can be helpful. So if you remember one, then you help you remember which order the other one is in. Okay? Alright, so here we're going to analyze an inverse trig graph. Okay, so analyze, we want to look at like where critical values are and where any points of inflection are and stuff. So, first of all, we have here arctangent of x quantity squared. So to get the first derivative, I know it's down there below, but think through how we would get that. We're going to do the chain rule. So it's 2 times the arctangent of x to the first, because the square is the outside function, times the derivative of arctangent, which was again 1 over 1 plus x squared. Okay? Now we've got to do the second derivative. Okay? If we want, we can go ahead and write this 2 arctan x over a 1 plus x squared. So to do the second derivative, what are we doing? Quotient rule, okay? Quotient rule. So here's our u over v. So u prime is going to be 2 over 1 plus x squared. And our v prime is 2x. Alright, so when we're doing our second derivative, we've got u prime times v. V is just a 1 over, or sorry, is just a 1 plus x squared, minus u 2 arctan x times v prime. Okay? All over u squared. So we have a 1 plus x squared squared. Okay? So notice here, this is kind of nice. The 1 plus x squareds cancel out for this. And we'll also have a 2 in common. So we can factor that out. 2 times 1 minus x arctangent of x all over a 1 plus x squared squared. That's our second derivative. Okay? So now if we're going to analyze the graph, we need to consider, okay, where is the first derivative equals 0 or undefined? Okay? The only critical number that we're going to get actually is 0. Don't forget what the domain of arctangent is. Remember, the domain of arctangent is from negative pi over 2 to pi over 2. Okay? So with the critical values, think about, okay, where is tangent equal to 0 in that range? It's only when x is 0. Okay? Because the tangent of 0 equals 0. The denominator will never equal 0 because 1 plus a positive value is always, will never equal 0. Okay? So that's why down here you see the only critical number is 0. And we can use the first derivative test. Okay? We can use the first derivative test at 0. With our first derivative, we have arctangent of x over something positive, right? So let's think about this. Arctangent, we take angles from negative pi over 2 up to pi over 2. When we're at negative pi over 2 to 0, our tangent is what?
Negative pi over 2 over 2. Wait.
Hang on. Oh, wait. Sorry. You know what? I did. Our range here. Our domain is from is all real numbers. Okay. So arctangent only equals 0 once, and that's when x is 0. Okay. if we go down here though, if we plug in a negative value, when will the angle, or I'm sorry, if you plug in a negative value, the tangent of what ends up being negative? Well, it's got to be the tangent of a negative is a negative, okay? And then if you plug in something above 0, you get a positive. So that's how we're getting a relative minimum at 0, okay? And in fact, if you plug 0 in, arctangent of 0 is 0, squared is 0. So the origin actually is the minimum, okay? Then you do the second derivative, and we could find the points of inflection. The points of inflection are when the numerator equals 0. Okay, that's only going to happen when what's in the parentheses there equals 0. Okay? And you can use the calculator for that. Okay, but we would find that it's x is positive or negative 0.765 if you used your calculator to see where the 1 minus 2x arctangent of x equaled 0. Okay, I lost a 2 up here. Okay? And then you can plug things in, and then also we can also see where horizontal asymptotes might be. Because you know arctangent had horizontal asymptotes, it'd be helpful to check for horizontal asymptotes here. Our arctangent has the horizontal asymptotes at y is negative pi over 2 to pi over 2. So because our arctangent was squared, it's going to always be positive, okay? But you'll notice here, if you look at the limit as x approaches a positive or negative infinity, arctangent is approaching pi over 4, so it's pi over 4 squared, okay? And then you can see, or I'm sorry, it's approaching pi over 2, and pi over 2 squared is pi squared over 4, okay? And then here you can see it's graphing everything that we have, okay? So pi squared over 4, here's our horizontal asymptote, okay, that we're approaching, y equals pi squared over 4. Here's the minimum at 0, 0. And then here are those points of inflection at the plus or minus 0.765. Okay? So that's one analysis. Notice the application really hasn't changed. We're doing the same stuff we did with all of our other functions. We just have new functions we're capable of doing it with. Okay? Another application is optimization. Okay? So here, notice what we've got is we've got a photographer. He's taking a picture of a 4-foot painting hung in an art gallery. The camera lens is 1 foot below the lower edge of the painting. How far should the camera be from the painting to maximize the angle subtended by the camera lens? Okay? You guys have all taken pictures. You know, you get closer, you back up, and you can either fit something in your frame or not. Here we're trying to maximize that angle. Okay, subtended just means that's how we can view from the top to the bottom. Okay, so you'll notice here what we have in this picture. Theta is the angle up from a horizontal. Okay? alpha, as they've drawn it here, alpha is the angle from the lens. Here's the perfect horizontal. So the angle up to look at the bottom of the frame is alpha. Theta is the angle to look up to the very top of the frame. Okay? So the angle we're trying to maximize is the difference between those. Okay? And that's that beta. This B looking thing is a beta. It's just 3 Greek letters. Okay? So that beta is what we are trying to maximize. Now, if we think about this situation, we're trying to maximize it by adjusting X. Okay? We're not tilting the camera at all or whatever. We're just trying to adjust how far the camera is away from the painting. And this is where, again, as we saw with optimization before, sometimes just getting the correct equation is the most challenging part. Okay? So how do you guys propose that we might find some kind of a function for beta?
Maybe tangent, like arc tangent.
Okay. We've got opposite sides, right? With this 1 and the 4, and we have this adjacent. So yeah, the arctangent looks like it's going to be helpful. By the way, don't feel like you have to write the final function all in the first step. Notice over here, the first thing that's written is just theta minus alpha. Sometimes, even though that's very simple, it's helpful to see because it helps you break down the problem. Okay? So, how do we find theta? Well, let's look at this situation again in relation to theta. Okay? So here's our angle theta. This is x. And we're measuring from the horizontal all the way to the top of the painting, which is a total of 5 feet. So that means tangent of theta is 5 over x. So theta is arctangent of 5 over x. Okay? So now if we're trying to write this beta as a function of x, we already have part of it. We have arctangent of 5 over x. Now we need to subtract alpha from that. Okay? So let's draw ourselves another little triangle with alpha. Okay? That's terrible. Let me try this part again. That's a little better. Okay, so here's our alpha. This again is x, but now this side is only 1 foot because we're just going to the bottom of that picture frame. So tangent of alpha is going to be 1 over x, which means alpha is the arctangent of 1 over x. Okay? So now I have the second half of my function beta of x is arctangent of 5 over x minus arctangent of 1 over x. Now it's just a matter of finding the derivative. Okay? So we got to find our derivative. Take a moment and try to do that part on your own. Okay, so the integral of arctangents u prime over u prime over 1 plus u squared, right? So what'd you get for arctangent of 5 over x?
Well, I tried like to making it like 25 over x squared inside, like 1 over 1 plus 25 over x squared.
Okay. So you have a 1 plus 25 over x squared on the bottom. On the top you should have a negative 5 over x squared, right? Because it's u prime over 1 plus u squared. Now, what's a quick and easy way of simplifying that?
Times by x squared.
Alright, multiply the entire thing by an x squared over x squared. And that'll cancel out. Remember, if you have complex fractions, you can multiply by the common denominator, which in this case just happens to be the only denominator. And then that part is going to be just a negative 5 over x squared plus 25. Don't forget to distribute on the bottom. But that's an easy way of simplifying that part. Okay? But that's just half of it. Then we have minus the integral of arctangent of 1 over x. So negative 1 over x squared over 1 plus 1 over x squared. And this you're doing the same thing. Multiply everything by x squared over x squared. And look at what you end up with. You have minus a negative, so I'm just going to make that plus now. 1 over x squared plus 1. Okay? And this is d beta dx. Now what am I trying to do?
Make it equal to 0.
Why am I setting equal to 0?
So that you can find, like, find the critical point.
Find the critical point so I can find the maximum. Okay, good. Find the critical point so I can find the maximum. Don't forget why you're doing this stuff, okay? Now, if I'm going to set this equal to 0, then I'm going to multiply both sides by both of the denominators. Or you can think of it as getting a common denominator. Either way, okay, I'm going to multiply by an x squared plus 25 and an x squared plus 1. And I do that here. And I also do it here. Okay, and the whole point is I cancel out that denominator, I cancel out this denominator, and now I have a negative 5x squared minus 5 plus an x squared plus 25, and that still equals 0. And now it's just a matter of solving. I've got a 20 here, I'll take the x squared to the other side, I got a 4x squared. X squared is 5, so x is plus or minus radical 5. Okay, I know it can't be negative because if I put I'd be putting the camera outside the building. Okay, on the other side of the painting, we'd be looking the wrong way. So I know it's got to just be a positive radical 5, or it's about 2.2 feet from the wall. Okay? Does that all make sense? Okay. Now, in order to do that, yeah, please don't forget that all the calculus that we do is in radians. Okay? So, when I then go to find beta of x, remember, it says, how far should it be? So actually I have already answered the question. Okay? We've already answered the question. That's it. But just to kind of close this whole thing out, we could then go ahead and find beta of radical 5. And it would be approximately that 0.7297 radians. that's going to be the biggest angle that we can get, or that's going to be the maximum angle that we can get there. Okay? Questions? Okay. So, again, just remember, every time we're doing derivatives with different types of functions, all the applications are the same. We're doing the same stuff we've been doing all year with derivatives, just new functions to do it with. Yeah, pay attention to the pictures. Here, notice theta is the angle. This person is standing still, and the airplane is flying this direction, okay, horizontally. We're looking at the change in the angle. You could think of it as, if you're standing there watching it fly over you, you're having to, you know, lift your head up, you know. What's the rate of change in the angle you have to lift your head up at? And then here, angular rate of change again. Okay, here it's a free fall experiment. It's dropped from a height of 256 feet. And again, you have this camera that's watching it drop. Okay. By the way, find the position function. Don't forget about our free fall. Okay. Our initial velocity is 0, right?
Yeah.
So do you guys remember our velocity function for a free fall?
16x squared.
For feet. So this one would be 4.9 t squared is going to be our velocity. And it's actually negative because it's dropping, right? So negative 4.9 t squared. What would the position function be? We're kind of doing this first part. Or how would I do it? I'll let you do the rest of it.
Integrate.
We're going to have to integrate it, okay? Integrate your velocity. And don't forget to take into account that we're starting 256 feet off the ground. Okay?